So this is another energy, momentum, then energy problem. This one is actually not as complicated as the other one, and so this could be on a test. In fact, we did have a problem like this on one of our first tests, I think, or our second test. So what's going on here? Block A is at a height. It's pushed down the smooth ramp. I'm assuming the horizontal part of the ramp is also smooth. It doesn't give a coefficient of friction. And then A hits B, and then after the impact, they come apart. B goes to the left, A goes to the right, and then B goes into the spring and compresses the spring. And they want to know how much the spring compresses. So from A going down the hill to just before it hits B, that's an energy problem. Before the impact and after the impact, that's momentum and coefficient of restitution problem. And then finally, after we know the velocities, finding the compression of the spring is another energy problem. So let's do this. Okay, and so the first part is an energy problem. We're given the height is 12 feet. So the potential energy is the weight. I think it was a 100-pound crate times the height of 12 feet. Afterwards, it will have zero potential energy, but 1/2 mv squared. The mass is 132.2. Solve for VA. We've done this several times. I can already tell you that the V of A just before impact is the square root of 2gh. Okay, so we know the velocity just before impact. Now it's the momentum impact problem. And so momentum is conserved in an impact. And so I've drawn before and after in terms of momentum. Let me write the mass in there. So the momentum before equals the momentum afterwards. So the momentum, I'm going to take left positive, MA times VA before, and afterwards, MB, VB2, 2 meaning afterwards, to the left, and MA, VA2 to the right. There are two unknowns, V of B and V of A, so we need one more equation, and that equation comes from the impact equation. So the velocity together, okay, is VA, right? Because VA is approaching B, so that's the velocity coming together. That times the coefficient of restitution, which is 0.5, will be the velocity going apart. So they're going apart at just half the velocity they were coming together. And the way I've drawn it, since I've drawn them apart, the velocity going apart is VB2 plus VA2. Those are two equations for two unknowns. You can solve for VA2 and VB2. Once you solve for VB2, you can figure out how much the spring compresses. So before, the energy is all kinetic, 1/2 m VB2 squared. And so that's this right here. That's kinetic energy. Afterwards, when the spring is fully compressed, the velocity is 0. So all you have is 1/2 k delta x squared, and solve for delta x. And it was nice. This problem said it was initially not compressed, so you can just get delta x directly. And so there you go. This is another energy, momentum, then energy problem. And this one we actually had on a test before, a variation of this.